All right, we're going to go ahead and get started. This is going to be the first unit in chemistry that's actually really chemistry type stuff. And it's not going to be as heavily focused, thank you so much, on math. So it's going to be much more concept intensive. So if vocabulary is not your strong point, this might not be so good for you.
Is it on RunWeb?
It is up on RunWeb already, the notes are. And I know normally we start class with like a warm-up, but today I'm going to give you the warm-up questions, and we're going to kind of answer them as we go along. So.
Wait, what week do you want? So just go to supplemental documents or what? Or lesson plan? It's in the lesson plan.
It's in the lesson plan, my friend. So here are your warm-up questions. I'm sure, like, for example, number 1, describe the 3 major states of matter. I'm pretty sure you could probably do that now. You might not get all the descriptive factors to it, but I'm pretty sure you can get close to it. What is the 4th state of matter? Where would you find it? We'll talk about that. What is meant by a change of state, and what are the 6 state changes? And then differentiate between chemical and physical properties and give examples. Some of these things I'm pretty sure you can do right now. Some of them, though, I think we should probably go over a little more in depth. So again, today, this unit is going to be much more vocabulary and concept intensive. So if math is not your strong point, yay concepts. If math is your strong point, sorry vocab. Okay? So everybody got that?
That's really cool. How do you do that?
Magic.
Oh, yeah.
Says, what is chemistry? Well, the definition of chemistry is the study of matter and the changes it undergoes. So the changes in which happens to matter. So what's matter anyway? Matter is anything that has mass and takes up space. Now, in our last unit, we talked about SI units. What is the SI unit for mass? Kilograms. What are some other ways to measure mass? Besides kilograms, what's something else?
Pounds.
Sure, pounds. That's the
Grams.
English equivalent. Grams. Sure.
Megagrams.
Megagrams.
Picograms.
Picograms. From the...
Gigograms.
Huh? Giga? Or giga. All right. What does it mean that it takes up space? How do we measure something that takes up space? What do we call that? Volume. Perfect. So what was our measure? What was our SI measurement of volume? Meters cubed. You'll never forget that, will you?
No, I won't.
Meters cubed. What's something? What if I don't have a solid?
Liters.
Liters or milliliters? These are all ways we can measure volume. So, again,
water, right?
Yes, I did. Thank you. There's going to be 4 main phases of matter: solid, liquid, gas, and plasma. We're going to focus primarily on these first 3. Solid, liquid, and gas. So there are 4 phases of matter: solid, liquid, gas, and plasma, and we're going to focus on the top 3. Michael, you okay? Did your computer die? Sorry. Hesper's sitting up front today. So we look, the first one we're going to talk about is the solid. Notice it says in a solid, particles are packed closely together, and they're held rigidly because they're bonded to one another. It's going to have a definite shape and a definite volume, and the particles can vibrate in place. Later on this year, we're going to talk about something called the kinetic molecular theory. What does kinetic mean? Movement, perfect. So the kinetic molecular theory talks about the movement of molecules. And from this idea, so we say that kinetic means movement. So from this idea of the kinetic molecular theory, we get this idea that the particles in a solid are vibrating in place. And someone in the other class said, well, how is it that they have a definite shape and definite volume and they don't go anywhere, but they're still moving? They're vibrating. And that doesn't mean, I gave examples like perhaps you're having a seizure in your chair. You're remaining in your chair, you're still vibrating in place. It's not like I'm asking you to shake all the way down the hall, right? You're not going to vibrate all the way down the hall. So the particles are going to vibrate in place. So even things like your desk, the floor, those particles that make those things up are all moving right now. You just can't feel it because the vibrations or the kinetic energy of it is such that it seems like it's standing still. But these things tend to be very rigid. Our next one is the liquid. Liquids is when the particles are packed closely together, but they're able to flow past one another. What that means is that we have those same types of things. We have those particles just like we had in a solid, but now instead of them being held in place, think of it if you had in a solid, you're attached to your partner with a piece of Velcro, and you're Velcroed onto them. Well, in a liquid, you would be held in place with like a long jump rope. So you could move past one another. So that's what it means that they're able to flow. And we say that liquids, one of their properties is that they have the ability to flow, and those molecules are going to move past one another. It has an indefinite shape, but a definite volume. What that means is that I have a Diet Dr. Pepper in my fridge. It has a volume of 500 milliliters. It has a shape of the Diet Dr. Pepper container. Now, if I wanted to be extra fancy and pour it into a glass, it would still have the volume of 500 milliliters, but its shape would now be of my glass. If I wanted to give my dog a treat and give him some of the Diet Dr. Pepper, no animals were harmed in the filming of this class, then I would pour it into his bowl, and it would take the shape of his bowl, but it would still be 500 milliliters. So solids have a definite shape and a definite volume. Liquids now, they have an indefinite shape, but they still have that definite volume. The third state of matter are gases. This is where the particles are not packed closely together. So instead of being held to your partner with Velcro back to back like you guys were a solid, or being held together by a long jump rope if you guys were liquids, you guys are now only held together by the intrinsic bond that joined you, the bond of the mind. So now you guys can move all around the room, but you're still partners and you know it. So these particles are not packed closely together at all. They're going to move and continue to fill up the shape of the container they're in. In this case, it would be the classroom. And they have no definite shape and no definite volume. Plasma is where we start talking about things in this highly excited electron state. And we'll talk about this when we do electron configuration, and you'll find out what it means for an electron to be excited. But just know that plasma is the fourth state of matter. About 99% of the known world is made up of plasma, but we're not going to do anything with it in class. So basically, we're going to focus on the 1%. Sorry, guys. An example of something plasma would be like the sun or a flame. So when we do our chemical and physical properties and chemical and physical changes lab later on this week, you will get to use a form of plasma. It will be the flame from the Bunsen burner, not burger. I know you guys all know how to light the Bunsen burners too, right? Do you remember how?
Yes.
I hope so. Well, this brings us to this idea of chemical and physical changes. Right now, the definition of a physical change is something that does not change the chemical composition of a material. This means you don't change the identity of it. You're not changing what it is made of. A chemical change results in a change in the composition of the substance, and thereby changing the identity of the substance. So what does that mean? Well, let's take a look at physical changes first. Physical changes tend to be your phase changes. Things like boiling, freezing, and melting. There are more phase changes. Let's see if we can't go over these real quick. What were the 3 states of matter? Oh, that's right. Thank goodness you remembered. Solid, I'm going to draw it out like this. Liquid, and gas. What is it called when you go from a solid to a liquid? Solid to a liquid is what? What is that called, that process? Melting. Fabulous. What is it called when you go from a liquid to a solid? Freezing. Awesome. What is it called when you go from a liquid to a gas? Evaporation or vaporization, not boiling. Vaporization. I'll write evaporation because that's a term you know, but know that vaporization. Evaporization. Okay. What is it called when you go from a gas to a liquid the other way? Condensation or condensing. Solid to a gas, absolutely. A sublimation. And then you what? What did you say? And then you don't know? I'm going to feel so good that I can teach you something today. Solid to a gas, or gas to a solid is called deposition. Now, going from a solid to a liquid, I think we're pretty comfortable with, right? Going from a liquid to a solid, I feel like you guys can all think of some examples for that. Going from a liquid to a gas and a gas to a liquid, again, I feel like you guys are probably pretty comfortable with. Now, going from a solid directly to a gas, this means you do not go to the liquid state. You do not pass go. You do not collect $200. You go directly into the gas phase. So solid to a gas, we said, is called sublimation. Iodine is absolutely one thing. Solid iodine. But the biggest, best example of it, something that pretty much all of you I know have seen, and if you haven't seen it, you probably will be seeing it in the next month or so just because of the time of year. Dry ice. And the ice I put in parentheses, or brackets or whatever, quotes, because it's not really ice. You know, ice is made out of what? Water, which is dihydrogen monoxide, or 2 hydrogens and 1 oxygen. Dry ice, on the other hand, is actually solid carbon dioxide. Thank you, Daria. It's solid carbon dioxide. And when you get that block of dry ice and you set it out, it looks like it's smoking. It's giving off a spooky gas. It's really just giving off carbon dioxide. What would happen? Well, there was an old episode of CSI where the girl was a chemistry major and she stole a bunch of dry ice and she put it in the vent of her romantic rival, and the girl ended up dying. Do you know why the girl died? Well, what happens when you inhale too much CO2? Yeah, your body's deprived of oxygen. Hemoglobin, the molecule that carries oxygen around the body, has a higher affinity for carbon dioxide than it does oxygen, which means that it's going to more readily bond with the carbon dioxide than oxygen, and essentially you will suffocate to death. So it was a really cool kind of thing because the dry ice disappears. There's no weapon left. You just have these bodies that look like they've suffocated, but how? There's no marks on the body. You know what? I would like to. CSI just ended last night forever. So
I know.
But
I was like,
yeah, so it was very sad. But you know what? I'm not sure I could even find it on net. It's not on Netflix.
Because it always has
crime scene. CSI crime scene investigation now.
All right.
You'd be able to watch it.
Maybe. Deposition is going from a gas to a solid. What word do you see in deposition?
deposit.
Perfect. Deposit. The classic example of this is going to be, well, what happens in the wintertime when you park outside? What do your windows look like? They don't get foggy. What do you have to do to them? You have to scrape them, the frost. Yeah, so deposition will be frost. What that is, that frost is when we have water vapor. Water vapor is just the gas form of water in the atmosphere. And it hits that very cold car window. As it hits that cold car window, it's going to go directly from the gas form to the solid form, right there on your windshield. Let's throw that guy over there. So, our physical changes. So boiling, freezing, melting. Oh, I have another question for you about this. I'm not so good at this. You guys have to help me out a lot. I'm sorry. What's the boiling point of water? So I've got, you gave me one of them, 100 degrees Celsius, 212 Fahrenheit, 373 what? Kelvin. Okay. Again, notice the degrees C and the degrees F, but the Kelvin, there's no degree sign.
Why?
You just don't, there's no degrees Kelvin. It's just Kelvin. Kelvin's the beginning. That's what all standards are measured by. What's the temperature of the condensation point? The ice melted and the beaker dropped into the other beaker. What would be the temperature of the condensation point? Huh?
Same.
It is the same. Why does that make sense?
Because it's just
Right, so either way you go, it's going to be the same temperature. So by that token, what is your freezing point of water? What temperature is the melting point? The same. So your boiling point and your condensation point are the same thing. And the freezing point and the melting point are the same. It's important to know that the freezing point and the melting point are the same. Now the other class asks, will there ever be a situation where something could coexist as more than one state of matter? And that happens all the time. Like when you have a glass of ice water. You have both ice and liquid at the same time. What is the temperature of a glass of ice water? It's written up there. 32 degrees Fahrenheit or 0 degrees Celsius or 273 Kelvin, ideally. Now it's going to be a little bit different because we have something called colligator's properties with all of the things that are dissolved in it. But that's the idea of it, is that's about where it should be. When will all of it be ice? When it gets below 0 degrees, right? When will it be all liquid? When it gets above 0 degrees. So until the temperature changes from that, so what's going to cause that temperature change is that if it's all solid and it can't go up to 0.00000001 until we have broken all of those bonds that are holding those rigid solid molecules in place and turning them into those liquid interactions, allowing them to flow past each other until every single one of them has been broken. It won't go solid until we've slowed down those liquid molecules. You remember the ones that are flowing past each other? We said that's one of the properties of a liquid. Until we've slowed them down enough until those rigid interactions, those stronger bonds in a solid can form, and it's thereby going to allow the temperature to continue to drop.
0 degrees Fahrenheit.
0 degrees Celsius.
Are you recording this?
I am. So another thing, so the physical change, the phase changes, you guys got those in the bag. You know those 6 things. What about a physical change would be if I were to cut something. If I take a piece of wood or a tree and I cut a branch off, it's still made of the same thing. It's still wood, it's still that tree. If I were to take a piece of wood, the same tree branch now, instead of cutting it off and I'm going to bend it, that's still the same thing. It's still a tree. It's just a physical change. Again, if I melt an ice cube into liquid, it's still made up of 2 hydrogens and 1 oxygen. The chemical composition does not change. It's just a physical state change. Chemical changes, on the other hand, are irreversible. And there's always going to be these key words to let you know. So they're going to say things like burning, cooking, decomposing, digesting, spoiling, or reacts with some other chemical. So a great example for this is, let's say that I cook scrambled eggs for breakfast, but I've made too many. I used the whole container. And then later that afternoon, I decide to bake a cake. All I need are 3 eggs, but I used all my eggs making scrambled eggs. Thankfully, I have leftovers. So that's a chemical change. I can't go ahead and take those scrambled eggs that I made at breakfast and throw them into my cake batter and think they're going to work the same, even though they're eggs. Because a chemical change has occurred. Remember in biology, what happens when you heat up a protein?
The bonds break.
Bonds don't break.
Oh, they change.
They change the bond. What do we call that? Perfect. You denature that protein. So the protein's going to be denatured. And in some cases, we're going to go from, remember that quaternary structure where it was a big globular protein, and we're going to stretch it out into the primary structure of the protein, the long chain of amino acids. So once you go from a globular structure to a primary structure, they're not going to act the same way. You've done an irreversible change to it. So how can you tell if something is a chemical or a physical change? When you're looking, usually on your homework or you're reading, what they're going to do is they'll give you some key terms. One of them is a color change. When you did the identification of unknown substances lab, you had a couple of clear solutions. In those clear solutions, if you mixed one of them with another one, you ended up with a white jelly-like substance in there. What that was is you ended up with a color change. So if you took two clear substances and it came out with something white, it was a color change, and that was indicative of a chemical change. A color change could also be written as the formation of a precipitate. And the precipitate is that solid, usually a different color, that's going to fall out of solution. So if I say, if it precipitates, what do they mean by that? It's raining. That means that liquid is falling out of the sky. In chemistry, when it precipitates, what that means is that a solid is falling out of your liquid solution. Another example of a chemical change would be smoke formation. Which one of those key terms on the last set of slides do you think that smoke formation is most closely related to? Huh? Burning? Yeah, burning. So a chemical change with the smoke formation, usually they'd say something burns in the presence of something else. Bubbling. This bubbling is usually indicative of a gas formation. So it usually indicates a gas forming. So it's another way to tell you that a chemical change has occurred. That's what those bubbles are. A change in smell. Think about burning a tree. It smells like s'mores. Remember, though, there's going to be some exceptions to every rule. For example, dry ice, we said appears to smoke, but we know that's just a phase change. Remember, it's subliming. Boiling water appears to bubble. It's really not. Oh, it is, but it's not the same reason. It's not a gas formation. So that's, again, just a state change. So things to remember about your changes is a physical change is a change of the form without the substance changing its identity. The composition is going to remain the same throughout. So if I had H2O solid and I added heat to it, I would end up with H2O liquid. I still have the same chemical components. I have 2 hydrogens and 1 oxygen. 2 hydrogens and 1 oxygen. It's the same thing. So a lot of times when you're thinking of physical changes, just try to think and remind yourself that physical changes most often are going to end up being phase changes. Chemical changes, on the other hand, change the identity of a substance. The composition changes and the products have a different property than what they started off with.
Like sodium chloride?
Yeah, but an easier, I think, one to think about that most people would know is, what if I gave you this? Nope. What is that the chemical equation for? That's cellular respiration, and cellular respiration is really just a combustion reaction. This is a chemical change. What we do is we take our monosaccharide, in this case we'll take glucose, so we take in the glucose in the presence of oxygen and it's burned. You burn it off. You break the bonds to get the energy out of it. And what you end up with, your products are carbon dioxide and water vapor. In this case, we've taken a solid, which we started out with, and we've turned it into two different gases. The property of that solid glucose is totally different than the properties of carbon dioxide and water vapor. So a physical change is going to be a change in state where you still end up with the same thing. A chemical change, we're not going to end up with the same thing. And we're going to have a complete change in the properties. So how do you know if a change is going to be physical or chemical? Things to look for. Physical changes can be reversed. Now granted, if I cut my hair, I'm really not going to attach the same hair to it again, but it's still my hair. If I melt ice, I can always refreeze it. Chemical changes cannot be reversed. You're going to see things that are going to say a color change, the formation of a gas, evolution or absorption of heat. What do I mean by the evolution of heat? If a chemical reaction is taking place and heat is evolved, evolution means change. It means that it's going to be given off. What about, it says, or a heat is absorbed. If you were having a chemical reaction take place in a container and heat is absorbed, what would happen to the container? If heat is absorbed, it's going to go into the reaction and the container is going to get colder. So another way that we're going to be able to tell if a chemical change has taken place is going to be by the creation or the evolution or absorption of heat. Another way is the formation of water. Now that doesn't mean when ice melts, water is formed, that was a chemical change. So is that it about changes? Well, no, it's not. Changes, we can also say, instead of simply saying it's a chemical or physical change, we can either talk about if it is giving off or if it is taking in heat. But don't confuse the concept of heat with the idea of temperature. The definition of temperature is the average kinetic movement of the molecules in a substance. We say kinetic means movement. So it's the movement of molecules, the amount of energy given off by that. Heat, though, is the transfer of energy going from an area of high concentration to low concentration. Where have you heard that before? Diffusion. Very good. So just like diffusion, it's going to go from an area of high concentration to an area of low concentration. And we're going to talk about this more a little bit later in the unit. Insert evil laugh here. So what do I mean by that? Those different changes in heat. I'm sure you've heard this before. We have endothermic and exothermic. But we're not going to call it heat anymore. We're going to call it enthalpy. Enthalpy. It sounds like I have a speech problem, but I don't. Enthalpy. I'll write it right here. Enthalpy. Enthalpy. In an exothermic reaction, heat is going to be released during the reaction. If you have someone who is your ex-friend, they have been released from the friendship. They've gotten out of your life. So in an exothermic, therm means heat. So we are releasing heat energy. Yes, sir.
Can I please a question quickly?
Absolutely. When this takes place in a container, your container is going to get very hot. That's because the energy that was in that reaction is being released to what we call the surroundings, and it's going to cause the temperature to increase. We're going to signify enthalpy with the capital letter H.
I think it's it.
Might be. So enthalpy is going to be signified by the capital letter H. What does the delta mean? Change. So delta H, or the change in enthalpy for an exothermic reaction, is going to be negative. So you'll have a negative delta H. Endothermic is the opposite. When we have our enthalpy is going to be absorbed during a reaction. And what happens with this is that the energy from the surroundings is going to go into the reaction. We call that the system. So we're going to go from the surroundings into the system, and the container is going to get cold. How many of you guys have had to use an ice pack before? Not one of the ones that came from the freezer, but the ones that you break and shake? You know, like the little bag ice packs? That's an endothermic reaction that's taking place. It allows you to go ahead and create that cold sensation with just a simple chemical reaction taking place. With an endothermic reaction, the enthalpy is going to be positive. So we have a positive delta H.
What do you mean by a change in heat being negative? Just being
Delta H would be like negative. So the heat energy in a chemical equation that it starts with, every equation is going to have a certain amount of heat energy that it has. And in exothermic, it's going to lose that. So when it loses it has to give it off to the surrounding area. So if you lose something, it's a negative number. So the delta H is going to be negative there. And if something is going to be positive delta H and the surroundings get cooler, what that means is that we've taken heat energy from the surroundings, and we've sucked it into the reaction taking place, and the container feels colder. So just to remember, if heat enters, it's endothermic, it feels hot. Or not hot, I lied, cold. If it's exothermic, heat exits and it feels cold.